Imagine a closed three-dimensional space. If every loop in that space can be continuously shrunk to a single point, does that space necessarily have the topological structure of a three-sphere? This question, posed by Henri Poincaré in 1904, remained unsolved for a century, defying the world's best mathematicians. The difficulty lies in generalizing the intuitive two-dimensional concept of a sphere's surface into higher dimensions. In two dimensions, any closed surface where every loop contracts is topologically equivalent to the surface of a ball, known as the two-sphere. Extending this certainty to three dimensions requires proving that simple connectivity is the sole defining characteristic of the three-sphere among all three-dimensional manifolds. The two-sphere, denoted S2, is the set of points equidistant from a center point in three-dimensional Euclidean space. Topologically, S2 is a closed, bounded surface without boundary. Its crucial property is simple connectivity. If you draw any closed curve on the surface of a basketball, you can slide and deform that curve until it becomes a single point, without ever leaving the surface. This property distinguishes the sphere from surfaces like the torus, or donut shape. On a torus, loops passing through the central hole cannot be shrunk to a point, meaning the torus is not simply connected. The Poincaré conjecture asks if this simple connectivity property uniquely defines the three-sphere, S3, among all three-dimensional spaces. A three-dimensional manifold, M3, is a topological space where every point has a neighborhood that looks locally like three-dimensional Euclidean space. These spaces are the fundamental objects of study in low-dimensional topology. Examples include the three-sphere, the three-torus, and various lens spaces. The manifold must also be closed, meaning it is compact and has no boundary. The conjecture specifically concerns these closed three-manifolds. If a closed three-manifold is simply connected, the conjecture asserts it must be homeomorphic to the three-sphere. Homeomorphism means there exists a continuous mapping between the two spaces with a continuous inverse, making them topologically identical.
Simple connectivity is formally defined using the fundamental group, denoted pi1. The fundamental group captures the structure of loops within a space. A space is simply connected if and only if its fundamental group is trivial, meaning it contains only the identity element. The identity element corresponds to the class of loops that can be shrunk to a point. For the three-sphere, S3, every loop is contractible, so its fundamental group is the trivial group. The conjecture is equivalent to stating that if a closed three-manifold M3 has a trivial fundamental group, then M3 is topologically equivalent to S3. The formal statement of the Poincaré conjecture is every simply connected closed three-manifold is homeomorphic to the three-sphere. This statement is unique to the three-dimensional case. For dimensions 5 and higher, the analogous statement, the generalized Poincaré conjecture, was proven by Stephen Smale in 1961. The four-dimensional case was proven by Michael Friedman in 1982. The three-dimensional case proved significantly harder because the techniques used in higher dimensions, such as handle-body theory, fail to provide sufficient control over the geometry of three manifolds. Simple connectivity is a property related to homotopy, which deals with continuous deformations of maps. A weaker concept is homology. Homology groups count the number of holes of various dimensions in a space. A space is a homology sphere if its homology groups are identical to those of a sphere. While every simply connected space is a homology sphere, the converse is not necessarily true in general topology. However, the Poincaré conjecture asserts that for closed free manifolds, being a homology sphere is equivalent to being a homotopy sphere, which is equivalent to being the three-sphere itself. This equivalence is what makes the three-dimensional case so powerful.
The solution to the Poincaré conjecture was achieved through the framework of William Thurston's geometrization conjecture, proposed in the 1970s. Thurston hypothesized that every closed three-manifold can be decomposed into pieces, each of which admits one of 8 specific homogeneous geometries, such as spherical geometry or hyperbolic geometry. The Poincaré conjecture is a direct consequence of the geometrization conjecture. If a manifold is simply connected, Thurston's program dictates that it must admit spherical geometry, and the only closed three-manifold admitting spherical geometry is the three-sphere. The mathematical tool used to implement Thurston's program was Ricci flow, a geometric evolution equation introduced by Richard Hamilton in the 1980s. Ricci flow deforms the metric of a manifold over time, smoothing out irregularities and moving the geometry toward a constant curvature state. The equation is a nonlinear partial differential equation analogous to the heat equation, diffusing curvature across the manifold. Hamilton showed that Ricci flow could often lead to a canonical geometric structure, but the flow frequently developed singularities, or points where the curvature became infinite, preventing the completion of the geometric decomposition. Grigori Perelman solved the singularity problem in Ricci flow. He introduced a technique called Ricci flow with surgery. When a singularity formed, Perelman demonstrated how to perform a controlled topological cut and paste operation, or surgery, to remove the singular region and continue the flow on the remaining pieces. Crucially, he developed a monotonic quantity, the reduced volume, which allowed him to control the geometry near the singularities and prove that the surgery process could be performed finitely many times, ultimately leading to the geometric decomposition required by Thurston's conjecture.
Perelman's proof, completed around 2003, confirmed the Poincaré conjecture, and more broadly, the entire geometrization conjecture. This result provides a complete classification scheme for all closed three-manifolds. Every closed three-manifold is now understood as being built from pieces that possess one of the 8 Thurston geometries. This classification is fundamental to understanding the structure of three-dimensional space, impacting fields from theoretical physics, particularly cosmology, to knot theory, which studies embeddings of circles in three-space.